Hello. The presentation that you are about to watch is from the HEC-HMS Calibration Workshop, recorded on April 8th of 2025. The material from this workshop is intended to help water managers performing HEC-HMS calibration to better inform their real-time flood forecasting. The workshop focuses on how to make models more lightweight and quicker, as well as various other recommendations and upcoming features that are focused on real-time operations. This presentation in particular focuses on the level of detail a model needs to perform well for real-time operations. The presenter that you will hear from is Matthew Fleming of the Hydrologic Engineering Center.
Topic is basically about the detail of your model, and is it too detailed for real-time forecasting? I have a question for you in a minute. You can start thinking about it now. We'll go ahead and ask it. So how much time do you typically have to create a reliable forecast? So that's the important part. So a reliable forecast. When you show up in the office in the morning, how much time do you have to turn out that forecast? So start thinking about that, and then we'll document some feedback from folks in just a second. But why calibrate? So the main reason is that reliability, right? So here we have a typical results plot from HMS, and we have the look back period. So this is where we have observed flow, observed precipitation, and we're trying to use that information and other information too, like observed snow variables, to train the model so that in the forecast period, so to the right of this dashed vertical line, that's the forecast period. That's when our observations run out, and we're using forecasted precipitation and temperature to predict runoff in the watershed, right? And so the reliable part of this is we want to make sure that the model is well tuned to the historical part of the time window, so that in the forecast part of the time window, we have realistic or reliable results. I've seen a couple of models that they rely on blending a lot to get accurate results in the look back period. Just want to caution that early on here, if you're relying on blending and not doing real-time calibration, then there's going to be little reliability in that forecast period. Okay, so let's get back to the question that we just asked. And I'm really interested to hear from you all. How much time do you typically have when you show up to the office in the morning to calibrate your model? And just take yourself off mute if you don't mind.
I usually have about 2 hours with the time I come in at.
Okay.
I'd say the same for Fort Worth District, mostly 2 to 3.
And I should clarify just a little bit. So it's more than just the flow forecast, right? You all have to make some really important operational decisions too, and relay that to operators. So in your time estimate, just through HMS, right? So how much time do you have for your flow forecast? I see an hour from Nolan. Does anybody have less than an hour to turn out a forecast?
We have a 4-day report that we have to put out for hydropower that has to go out by 8 in the morning, but it just depends on what time you get started.
Yikes. Okay, so you're not rolling in at 7:59 on those days?
Nope.
Yikes.
Yeah, up in Seattle, we usually have forecast or inflow forecasts from the RFC that we use in our models, and that allows for a quicker turnaround rather than using HMS. I think HMS is primarily used for flood and inundation maps, and we'll have a higher or a longer time window to get those turned around. Like the 2 to 3 hours that people have been saying is about what we could spend before clicking the compute button.
Okay. All right. So if you were trying to get an HMS derived forecast, you'd have about 2 to 3 hours to turn that out?
Yep, I think so.
Okay. Well, that's more time than I was thinking. So Amanda has about 30 minutes. Okay. So there's a shorter turnaround time for Amanda's watershed. Okay, well, some of the models that I've seen is it's going to be hard to turn around a forecast in an hour, even up to 3 hours, just because of the complexity of the model. So a couple of things before we dive into things to consider or changes to consider. It's a good idea to understand what you have to work with, so how much time you have to work with, so you can start making simplifications to the model or your workflow, and we'll talk about the differences there. And then one thing we'll focus on today, we're not necessarily diving into the nuts and bolts of calibration. We're going to save that for Wednesday and Thursday. But what we're diving into now is giving you more time to do that critical thinking. We're going to focus on changes you can make to your model to make it run faster, or to improve your workflow so you have more time to make those critical decisions about parameter changes. Okay? All right, so let's start from the top here. Time-saving changes to consider. And I'll send out my notes. These are my notes, and I have a couple of models that I'm going to kind of talk through. I'll send out these notes at the end of today. And if we need to add any to it, we can add to it in real time here. So the first thing here is reduce the number of calibration points in the model. The bare minimum, right? So your reservoir inflow locations, you want to make sure that the model is well tuned for reservoir inflow, and then at key points downstream. All right, so that's the bare minimum. And two things that you can think about, so there's two approaches that you can take here. Without going back to the GIS, so just staying with the model that was delivered to you or that you inherited, you can reconfigure the zones and how those zonal overrides are used to make adjustments to the model parameters. And here I have in the notes too, try not to use the element overrides, focus on zonal adjustments. Okay, so let's dive into some details with the model. Yep, here we go. All right, so what we're going to focus on here, so here's our Russian River watershed. There's a reservoir up here in the headwaters, so way up here. The water is moving down or to the south and then out to the ocean. And then there's another reservoir over here, okay? One thing that I noticed with this project is there's tons of gauges and subbasins on this tributary called the Mark West Creek tributary, okay? And so if I was looking for a way to reduce the amount of calibration here, I wouldn't have to necessarily go to each of these locations and tune the model at each of those locations, right? This is a tributary. The reservoirs in the system don't operate to this tributary, okay? They operate to the main stem of the Russian River. And so to save time, I could have within this tributary would be one zone, so just one zone, not a zone for each of these computation points or locations with observed flow. And then I would use the zonal adjustment to change all the parameters in this zone by one scale factor, right? So that would be a quick change. I can make that quick change and then really only focus on the results here at the outlet of this tributary. Okay, does that make sense? All right, so that's one approach. The other approach from the notes here is we could go back to the GIS and reduce the spatial complexity of the model, right? We could merge those subbasins together and then just have one subbasin for the entire tributary and work off of that, right? And so that's what I did in this other model, not that one. This one, let me turn off the grid as well. Okay, and now you see in this model, there's just one subbasin representing that Mark West Creek. For this approach, it's definitely going to run a little bit faster because HMS is not performing the calculations for each of those individual elements. It's only running the simulation for this one subbasin right here. Precipitation is being varied spatially because we're using the structured discretization and Maud-Clark transform. So we are getting that spatial variability. We're just not breaking it down into smaller subbasins. Okay. Any concerns or any additional thoughts about that approach?
Hey, Matt, what's the difference? How do they perform? You know, like that's always been I've seen districts where, yeah, they have it very coarse. They only have a delineation where they have a gauge. And then like one of our subbasins or one of our watersheds, there was like 200 or 300 subbasins in the watershed, and it was a nightmare, you know. And I figure something in the middle is probably a good idea, but I just wonder, you know, how well does it perform using just the grids?
Yeah, just using the coarser delineation.
Mm-hmm.
I don't have a good example for comparing the results here because I couldn't get the original model to actually run. But for here, let's see if I actually have viable results. Let's see. Oops. It's not pretty. Probably didn't spend that much time calibrating here, but why wouldn't I spend much time calibrating here is the overall contribution from this tributary to the Russian River is pretty small, right? And so I could get away with, if we look at the Nash-Sut cliff or some of the metrics here, and these are pretty pitiful, you could get away with lower metric values, percent bias and Nash-Sut cliff, because again, in the grand scheme of things, that tributary doesn't impact flows on the Russian River. If I was looking at these metrics and doing a real-time calibration, I would do better than this. But with the simpler model, it's going to help. It's going to afford you the time to improve those metrics much faster. The other thing I wanted to highlight with this model too is the way that the zones were configured. And we'll probably talk more about this tomorrow. All right. So in this model, we have this zone here, the middle zone. And you can see when I select the zone in the upper table, this is my zonal override table. These are all the elements that are associated with that zone. So just a quick guess, about 15 subbasins live within this middle zone. In my map, so let me select those subbasins. So we go from Feliz Creek, let's see here, Feliz Creek down to Healdsburg Local. That's about right. About right there. Okay, so let's train our eyes to the middle portion of this watershed here. And so what I noticed in this area, there is a little tributary that has observed flow, and there's a number of locations along the main stem that have observed flow. Okay, so if you wanted to, you could use these element overrides. So you could click on, so Big Sulphur Creek here, you could click on that, turn that on, and start making adjustments just to that subbasin. And then look at the observed flow at that subbasin. Okay, so you could do that for this guy, and then you could work your way down through the 4 or so computation points just in this middle zone. You could do that. Or another way to approach this is not to touch the individual elements, but only change the zonal adjustment for all 15 of these subbasins. So I would just change that initial deficit to 1 for all those 15 subbasins, run the model, and then really only focus on the performance at this downstream point. So whatever that is, the Healdsburg gauge or whatever at the downstream end of this zone, only focus on that, right? So instead of improving the model incrementally as I work my way downstream, I'm going to make sure it does the best at the downstream point, but it probably does okay at those intermediate points, okay? So what I'm getting to here is instead of calibrating the model to 20 locations, you could focus it in on a select few locations while saving time. Any comments about that approach?
So Matt, maybe it doesn't matter, right? If you're just calibrating through so you can get your inflows at the next reservoir at your next control point, but maybe if you're running RAS through one of those reaches, you might care more about what your locals are.
For sure, yeah, that's a good point. If you want to get to a reliable inundation map, then you would want to spend more time on those tributary flows. Yep, that's a good point. If you're looking at getting to a result to help you with operations, that might be a little bit different. So I could see a workflow where if you need to turn out an answer pretty quick, that's one thing, versus if you have some time in the afternoon after you do the operations to get a more reliable inundation grid, you could spend more time on the calibration. Yeah. So if that's the need, then that would point towards not redelineating the watershed, not merging subbasins together, but being strategic in how you use your zones, right? So start lumping as many subbasins as you can within a zone to help you get through that quick forecast faster. And then you could maybe do your element overrides if you're trying to get to a better inundation map. All right, what else do I have here? Yeah, if you do need to merge elements together, one approach that I highly recommend is you can use ArcGIS or ArcPro to merge polygons together, right? So you could export your subbasin polygon layer and your reach layer, use the merge function in ArcPro, and then within HMS, you delete your old element. So let's say you want to merge 3 subbasins into one. You would just delete those 3 subbasins within HMS and use the GIS importer option in HMS to import just that one polygon that represents the merged subbasin, and then you link it up into your network. So that's the quick way of quickly redoing some of the delineation if you just want to do merges. I would recommend that approach. And if you're interested in that, just reach out to me and I can walk you through that in more detail. That's exactly what I did on the Russian River project. I didn't use the GIS tools to redelineate. I just used some merge options in ArcPro and then re-imported it. If you do a wholesale change to your geometry, this is kind of what Jody's doing right now on the ACF watershed, then you do have to go through a whole process to reparameterize and recalibrate. So that's kind of I would give that the nuclear option. You're starting over from scratch and you're going to redelineate everything. And if you do that, you're going to have to recut your reach information, reach lengths, your in values, your cross sections, and all that. So it's going to take a little bit longer if you go the nuclear approach versus using some tools in ArcPro to merge elements together. So there's pluses and minuses to both. All right, the next thing for saving computation time, or just saving the time in general to get a forecast up and going, rely on the forecast initial base flow and the forecast reservoir editors to set the initial base flow and reservoir elevation, so you don't have to do this every time you create a new forecast. And what I mean by this is one of my most favorite tools. Not this one, this one. All right, I have a forecast selected right now. And if I go to the compute menu and choose forecast initial base flow, this is the initial base flow editor. And what it does is for each of your zones, it gives you the subbasins in that zone. And then you can choose a gauge. So this is the easiest for those headwater subbasins, right? It's a headwater subbasin. There's a gauge downstream of it. And you can use that gauge. You reference the gauge to the subbasin, and what HMS does behind the scenes is it goes out to that gauge, it knows the start time of the simulation, it pulls that information from the DSS file, and then what it does is, so here's the observed value at the beginning of the forecast, 250 CFS. You can specify a ratio here, and the program will multiply this ratio times the observed flow. And what this means for a headwater subbasin is you would just use a ratio of 1, right? So whatever is at that gauge is what we want to use for the starting value for that subbasin. If you're working your way downstream, it gets a little bit different, right? So the ratio that you might use for, let's just pick an example here. So let's assume there is no reservoir in the model. We're just looking at this location here, the Hopland gauge location. And we chose, for example, we chose the Hopland observed discharge gauge as the gauge for all the subbasins upstream. So let's just say there's 4 subbasins upstream. The ratio that you would use is the incremental drainage area to the total drainage area at that point, right? And so if we had those 4 subbasins, this one might get 25%, 25%, 25, and 25. And the program would use that ratio times the observed value to initialize base flow at each of those subbasins, okay? So that's going to be a quick time saver for you. The one issue where it gets a little tricky is for your elements downstream, your subbasin elements downstream of reservoirs. In that case, you're going to have to go through a little bit of trial and error for what the ratio might be. But what I've found is once you have a good idea what the ratio is for this base flow adjustment, it's pretty consistent from forecast to forecast to forecast, okay? So spend some time getting familiar with the initial base flow tool. Another time saver is going to be from, again, the compute menu, your forecast reservoirs. And this is the same type of thing. You choose an elevation or a stage gauge for each of your reservoirs. And then what the program does at the very first time step of the simulation, it goes to that time series gauge and it pulls in the value from that gauge. And that's the value it uses to initialize the starting stage for the simulation. Okay. Yeah, Roberta.
Oh, I was just, one of the things that I use this for, particularly if we're in the summertime or something and you have to dry, I default to 0. Chances are that's the base flow. So it kind of depends on maybe the time of year. I might just go in here and set them all to 0, particularly if you don't really have a headwaters gauge, for example.
Right, right. I like that. Yeah, you can override. So the final value here is what you get to set. Yep. Okay. Any other questions or comments out there on those 2 tools that you can use to get the model up and running for a forecast?
Hey, Matt. On the when I first started doing this and I started using the initial base flow override, I would just use it for those headwater basins that had a subbasin and a gauge. And it wasn't until later that I finally went back and said, okay, well, I would just use the closest, individual subbasin, right? And use that to come up with that ratio and at least to get in the ballpark. And that made a huge difference. Yep.
Well, yeah, I could see that for your model. Your model it's a doozy.
Yeah. Yep.
All right, let's talk about this next topic. And this would be good for a lot of us. Have an array of basin models and forecast runs pre-configured that reflect the starting conditions in the watershed. Okay, I've seen a lot of SWMS models that have just one basin model, one MET model, and one forecast alternative. And what that means to me is every time you create a new forecast, you're probably going to have to do some significant adjustments to the initial deficit and other parameters too to reflect the current state of the watershed. You could reduce that initial setting of parameter values by having some kind of configuration where you have a basin model that reflects dry conditions, one that reflects average conditions, and one that reflects wet conditions. And what you can do is let's say, for example, for the dry basin model, for that basin model, your initial deficit, you would expect the initial deficit to be pretty high because you're assuming that it hasn't rained in a couple of weeks And so your initial deficit's probably greater than 1 inch. Your loss rates are going to be higher because, again, the soil is dry. And the base flow fraction parameters are going to be lower than average. Okay, so you could have that basin model ready, and anytime the conditions in the watershed reflect those dry conditions, you're just going to select that forecast alternative from HMS whenever you choose that forecast run from the CAVI for the forecast. Okay, so it's going to save you some initial time into having to go through all the basin models or all the zonal adjustments to get those initial conditions set properly. For average conditions, you would do the same type of thing, right? So for that basin model, you're assuming it's rained in the last 3 to 5 days. Your initial loss is between 1/4 inch to 0.75 inches, and so on. Okay, so this type of setup should save you time every time you create a new forecast moving forward. It should mean less parameter adjustments. Okay, any disagreement or agreement out there you want to talk about?
I wholeheartedly disagree.
Okay.
So what I have found just from personal experience is the easiest approach, or maybe the easiest approach for me would be, I have one average, like you're talking about, set of parameters, and I start with, I do a continuous HMS forecast through the entire season. So each time I don't create a new forecast, I take that forecast and I change it and I expand the time window. So the look back period changes and then the forecast time moves up. And then that's I've seen works the best for me in our basins as far as like trying to keep it calibrated. It's just when I go back and look at like when the SWMS models were developed, if you look at a lot of their calibrations, they're not always that good. Like you're looking at, oh, this is the best we could do. And when you're reading the report. So I find that, just that continuous forecast run is probably the easiest place to pick it up from most of the time. As long as you're consistent.
Okay. Well, you said some good things there. Let's dive into what you just said, Kevin. So I guess make sure I'm capturing this right. So you prefer one basin model, but then each day or each week, you're just extending the end time and the forecast date. Is that right?
Yep. And then I'll tweak the calibration as I go to match what it was observed from my last forecast to the current time.
Okay, so you're focusing.
Yeah, I'm trying to match that. I try to match the forecast, like the observed window as I expand, move forward in time. And then I use, really what I'm doing at this point is I'm just comparing to what RFC puts out for their forecast and how my forecasted flows compare to that with the HMS model. But I always start with trying to get the observed base flow and like if there was an event or whatever there was before that captured first with the calibration.
Okay. Does the runtime ever impact you? Since you're growing your time window, do you hit like 2 months of simulation? You're like, oh, this is taking too long. I'm tired of it.
I don't necessarily. So my start time, I don't always start from the very first date. I'll start moving my start time forward because that was actually one of the things that I was kind of curious about question-wise for this workshop was, so I find the longer my the longer my observed window is for my model run, the harder it gets to hit the in-betweens, like the events and the actual, what's one call it? Like how the basin is responding in between those is harder and harder to capture the longer that observed window is what I seem to find. So I'll just slide it in time and make sure I'm capturing the most recent basin characteristics usually. Try to at least have like 10 days or a week back.
Okay. One final comment. I totally agree that those models that were handed off, the calibrations could be iffy. But I think I would try to find time to make your own improvements to those, right? So you already have the data. You have some really good data. You could refine what the state of those models are to help build what you think are realistic parameter sets. So don't give up on them, I guess is what I'm trying to say. Take what you were given and make them better.
Yeah, well, like if you look at, so another thing that a huge trend, like something that changed pretty significantly from the time the models were built was the additional linear reservoir, which is a much better baseflow method for pretty much all of our basins. And so like my rogue model wasn't calibrated in that. So I'm starting from a fresh calibration anyways with a whole new baseflow method. So
Yep. Cool. Any other questions or comments out there?
Kind of curious
So-
what you recommend when doing multiple basin models. If you go in and have to change some of the base parts of that basin, how to make sure to properly copy that over to the other basin models.
Oh, usually what I do, Nolan, is I have a spreadsheet. I love spreadsheets. And I rely on the global editors in the, so let's see, let's open a project. All right, so within, if any basin model is open, you can go to the parameters menu and choose, let's just choose transform, Clark unit hydrograph, and you see that this table opens. And what I would do is I would have my spreadsheet with my best parameters and then just copy and paste into this table. Is how I would do that.
Gotcha. And I know I like rezoned one of my basins. I learned how to just copy and paste those between the basin files and the subdirectory and just stuff like that as I make changes.
Good. You know, one other thing to consider too, differences between dry, average, and wet basin models. I would expect different routing parameters between those, right? So for dry and average, you're probably going to have different time of concentration and storage coefficients. You're going to have different reach routing parameters between those and a wet model. Because I would consider your wet model is things are super saturated. When it rains, the depth of water on the land surface and in the channels is going to be greater. So your velocities are going to be different. And so I would try to carry through, think through the changes that you want to make to the base model that reflects all those conditions. And it's not just your initial states that you want to change between these basin models, it's also routing information too. Yeah, Craig.
I like spreadsheets too, so I have a lot of my parameters already set in a spreadsheet. And have you ever had issues where you copy and paste it over back into the editor? And I can't remember what errors that I actually got, but I was getting errors from copying and pasting the entire, row.
Yeah, let's see. One thing, I can't think of any specific errors, but one thing you have to watch out for is if I have this table open and I also have the component editor for one subbasin, so my Hopland local subbasin open, if I make a change here and hit save, it's going to update it in this table here, so it should. So where's my Hopland? Right here. So it's the fifth one. So this 8 should change to a 10. Okay. If I change this from 10 to, let's go to 9 and hit apply, it's not going to save because this guy is open right now. This component editor for the subbasin always wins. I believe. I think that's how it works. Let's just verify. So I changed it there, hit apply. Oh, it did win. There is a, let's see, let's just try again. 11. Oh, if I hit the save project button. Oh, it did. Okay, well, Craig, I'm not sure what I was thinking. I guess bottom line is just be careful of interactions between the global editor and the component editor here. I love it when the software proves me wrong. All right. Let's see here. Let's go to the next one. What we got?
I've got a question real quick, Matt, before we push
Yeah.
forward. So for your point there, number 4, there's a lot about that seems attractive to me in my approach to modeling. It's not one that I've done, but I guess my question there is if you've got a forecast that you're adjusting time for, and you're kind of maintaining your model with tweaks as you move forward in time. I'm not real familiar, like if you've got a forecast period, like you want to be able to save that forecast for this particular event so that later in time you can come back to it. I see like there's the ability to archive a forecast, but I'm not sure the best way to make that happen. And I don't know if my questions actually make a sense. Like, I may want, at the end of the year, I may want to come back and pull up that forecast that I ran for the rain event that we had this past weekend. But if I'm adjusting my current forecast and moving it forward in time, I feel like I would lose that.
Yeah, let me get Kevin back in on this one. Kevin, if you wanted to archive a forecast on a specific date, are there any issues with archiving it doing the method that you suggested?
Or do you even worry about it?
Not really. I mean, if I really, really wanted to archive those specific starting parameters, I would probably just zip it within the forecast alternative, the actual HMS model itself.
Okay. Mm-hmm.
That would probably be the easiest way. And then the other way, so Russ. Oh, sorry. Go ahead.
Well, I was going to say, like in the caddy underneath the forecast menu, there's actually an archive selection in that drop-down menu, and I've never noticed it before. I went looking for something as you were talking through how you approach it, with that question in mind, and I've just never seen it and I've never tried it.
Yeah, I don't think I've actually ever used that button myself. I usually, if I really want to save like current conditions, for whatever reason it may be, I just do the good old zip that HMS and then put it somewhere, save it. But also, and then so Russell Ehret's actually working on a script right now that is kind of like to replace the save from base for HMS parameters, so that you're actually able to keep like a stored condition, like the conditions like that, to be able to start from that state. So you can open up a new forecast and then import basically those conditions that you save in a separate spot to bring in. So that's
that would be sweet.
Yeah. So that I haven't started. He just handed over to me to start testing it, but yeah, that's I think what he has going on there, right, is probably the ultimate solution to what you're talking about. Is a good way to archive and maintain those parameters.
Okay.
Yeah, let's touch on that for a minute. Yep. So this is a really good topic, archiving and parameters. So one suggestion I would make is when you're calibrating in real time, you're not changing the base parameters. So you're not coming to this editor and making a change to transform, okay? I would keep all your base parameters constant and consistent from what's in the watershed model, the watershed directory model. What you're adjusting during a forecast is you're using those zonal overrides. So these adjustments here, and these sit on top of the base model, right? So you can see if I can find where's, maybe it's up here, no? Oh, upper. Right, so here's my Hopland subbasin. This is what's in the base model, 0.2 inches for the initial deficit and so on. If you change this to 0.4 for the zonal adjustment, then all 3 of these subbasins are basically going to use this 0.4 inches for the initial deficit. So you're not changing the base value, you're overriding it with the adjustment. These adjustments live, just if you're interested, within the HMS folder, the forecast directory. There are these files that end in forecast, and let's just choose one of them. You can take a look at these with Notepad or TextPad. And in here, you'll see that all of those zonal adjustments or the element overrides are going to be saved to this file. And that's what the script that Kevin was talking about that Russell's working on is. It's going to let you create an archive of all of these forecast.forecast files. And then anytime you create a forecast in the future, if you'd have a really good naming convention that helps you remember what this zonal adjustment setup, what it reflected, right? Maybe it's for a really large event or a rain on snow event. You'd have to work out your naming convention. You would be able to choose that .forecast file, and then those zonal adjustments are automatically going to be pulled into your new forecast. But it should give you a quicker starting place for those adjustments. All right. Step 5, or option 5 to consider here, only adjust your key parameters when calibrating. If you have your array of basin models, if that's the approach that you choose, then you don't have to really make those big structural changes. Your Clark parameters are going to be okay, your routing parameters are going to be okay, and for the most part, other parameters too. In that case, you can really only focus, or you really only have to focus on some key parameters here. And my bare minimum that I would suggest focusing on, if you don't have a snow model, if it's just a rain-only model, would be the initial deficit, your constant loss rate, and then the groundwater 1 and 2 fraction parameters. That's if you have linear reservoir baseflow. If you have the recession baseflow method, then I would only focus on that ratio to peak or that recession constant, or maybe both of those for the recession method. Okay, so you can really get it down to just 4 parameters if you have a good starting basin model for that forecast. Yep, and that's what we have in B there. So other parameters like your mod Clark parameters should only be adjusted yearly or be specific for the type of flood event that you're trying to forecast against. Okay, so hopefully that helps. It narrows it down to the number of tuning knobs that you need to change during a calibration. All right, and then the last one, we have a lot of sub-bullets here. Reducing the computational burden. The first one is the easiest. We kind of already talked about this. Make sure all your background shape files are local to the project. They live within the project directory. And also they have a small file size. I've noticed a couple of shape files out there that have tons of vertices in them, and it takes a hot second or two for HMS to draw or render those shape files. So if you use the GIS tools to clean those up or to simplify, then they're going to be drawn much quicker. And that's going to help you when you pan around in the basin model map. The other thing to work into your workflow is make sure you understand compute to point, and you make use of that in your workflow. Basically what compute to point does is, let's open up. Instead of, if I hit the compute button here, HMS runs all the elements of my basin model. Or I could start from the headwaters here and then right click on this compute to point option, and the model is just run to that point right there. So it should be much faster. So as you calibrate from upstream to downstream, just run to that computation point. Or if you're using the combined parameter editor from the CAVI, the trick is within the combined parameter editor, there's an option for you to choose computational points right here in the bottom left. And so you can start with your headwater computational point and hit the run button, and the program runs just to that point. Okay? So that's going to be a nice time savings for you. You can turn off the option for HMS to compute all elements all the time. So that's one of my favorite things to make sure is not selected. If you go to the Tools menu, Program Settings, under Compute, there's an option here, Compute All Elements, even if unchanged. I uncheck that. And what that means is HMS keeps track of edits made to each individual element in the basin and met model. And if you don't make changes to an element, then the results that are in the simulation DSS file, they're still good. So it doesn't need to recompute them. Okay, so if you uncheck that option, the model should run faster after it's already run one time and you start making changes to the model. Okay, what that means though, let's say I ran my entire model here and I make one change at one of these headwater subbasins. If I hit recompute, HMS for sure will rerun this subbasin right here, and then it reruns all the reaches that are connected to it downstream. All the subbasins are still valid. So it doesn't have to rerun the subbasins, it just reruns the subbasin that changed, so this guy right here, and then the reach network downstream of that point. All right. One thing that could help you, I've noticed a lot of models, when they were handed over, had really short routing reaches in there, Muskingum-Kunz routing reaches, and the reach length might be less than 10,000 feet. Okay. In the grand scheme of thing, if you look at the routing results from that reach that has a really small distance to it, you're going to see very little attenuation and lag. You're going to save yourself some simulation runtime if you just change that routing method from Muskingum-Kunz to null routing or no routing. So maybe a rule of thumb here is for reaches less than 10,000. Okay. Any agree or disagree on that one?
I was going to say the same thing as Paul in the chat. Got a couple places where I use lag routing still. I don't know how you feel about that, but
oh yeah,
it's not super hydrologically sound, I guess, technically sound, but it gets the job done in a forecast.
Right. I agree. 100% agree. Yep. Let's see here. You can experiment. I know part of the SOP for the MMC models as they were developed for HMS was to set the simulation runtime to 1 hour. But if you have a large model with large subbasin areas, you can experiment with the simulation time step. So try 2 hours or 3 hours and see what that does on the results. So see if the results changed and see how the runtime was. So if you had a drastic decrease in runtime, but the results had no change basically, then I think that's a move in the right direction. It's going to save you time when you calibrate your model. Okay. Any negatives to changing the simulation time step from 1 hour to 3 hours?
The only thing I could think of is it probably depends on how flashy your basin is. If you have really rapid changing hydrographs, I think that you might end up so I had to change ours recently from like 6 hour to 1 hour just because I wasn't capturing quite the peak of the event properly in my hydrograph. So that's the only consideration I could think of. I'm sure there's the desert-like places that have even faster flashes of peaks.
Yeah, that's a good point. So here's a little bit of clarity here. So if your time of concentration for your subbasins, if it's greater than 6 hours, then you can start experimenting with a larger time step. But if you have a flashy watershed where the time of concentration is less than 6 hours, then you're out of luck. You got to stick with a 1 hour time step.
So what if your time of concentration is like an hour or less?
Then you need a 15-minute
reservoirs.
15.
Yeah.
Yeah.
Because we've got one really that's probably it's probably sub 1 hour for one of our reservoirs.
Yep. That's the worst case
and
scenario, Ken.
Yeah.
And your model was the one I was thinking about, Ken. So.
Yeah. It's the Lacta one, where it's it's basically all urbanized. It's just pavement.
Yeah. Yep. All right, the next thing to consider is once you do have your model georeferenced and you have terrain in your model, then you can move away from the old Mod-Clark grid cell file and use the discretization option in HMS. In the discretization option in HMS, you can quickly change it between 2 kilometers and 5 kilometers and even 10 kilometers if you wanted to. So you can change the grid cell size that the program uses for gridded precipitation, loss computations, and Mod-Clark transform. All right, so let me get my example back open here. I'm going to turn on my discretization. Okay. So here we have a 5 kilometer grid cell overlaid on top of the subbasins. And so what HMS does with this grid here is it finds all the precipitation, so the gridded precipitation, and finds that for the grid cell. It does the loss computation, so based on your deficit and constant loss parameters, it computes how much excess and how much infiltration there is. And then it routes it to the subbasin outlet. Okay, so that's what's happening with Mod-Clark. So you can see there's going to be a different computational burden when you have 5 kilometer grid cells versus, let's go back to our original model. Here's 2 kilometer grid cells. Okay, so for that same subbasin, now we have at least 4 times as many computations per time step. All right, so that's going to be a little bit of a computational burden, so you can always experiment with those. And let's see, do I have a typo in my notes here?
I got it, Matt.
Oh, yeah. Oh, thanks. Yeah, that would be a large grid cell size. But when you make those changes, you can do what I did here. So let me go back to my model. You would have separate basin models, right? So here's my basin model with 2,000 meters, 5,000 meters, and using just the Clark method. The Clark method it doesn't do any of the gridded computations. What it does is it takes all the gridded precipitation, it computes the subbasin average of that, or the area weighted average of that precipitation, and then does the loss computations and the unit hydrograph. So Clark method is going to be definitely the fastest if you can get away with it, versus 5,000 meters Mod-Clark or 2,000 meters Mod-Clark. What you would have to do, though, is with a couple of events that you have in the watershed, look at the results and see if they change drastically whenever you go from one option to another option. Okay. When I looked at the Russian River watershed for this one event, what I noticed is the runtime. So you can always see the runtime at the bottom here. So I'm going to start with my 2,000 meter simulation. So it should be that one. Yeah. So 4 seconds, not bad. If I jump to the 5,000 meter, it's going to be about the same, maybe 3 seconds. Let's see. It's 4. And then the Clark method. It failed. I think I did something. Oh. Yeah, I did something to the reservoir. Let's see. Everything. 4 seconds. So in this very simple watershed, simulations between all 3 options were basically the same. And then I can check the results too. The fastest way to check the results is you just expand the tree for each of those simulations, choose a subbasin here. I'm going to choose the Capella for each one. And let's just choose alpha. If you hold down the control key, you can click on each one of these time series and it'll plot it. There's a difference between because the starting condition is not the same in all of them, but when you get to this event here, there's basically very little difference between these three different options. Okay. So in this example, this watershed, you could probably get away with CLRH for this one event. And the reason why is the precipitation is pretty uniform across a subbasin because these are pretty small subbasins here. Okay. This is not the case when we look at Paul's Osage model. That's a different beast. Let's see if I can get that one quickly open. Here we go. And so what I have in Paul's model is I have, let's see here, how to talk about this. I turned on spatial results for one thing. And the spatial results are turned on. These are 5-kilometer grid cells. So you can get a quick idea. This is a pretty large subbasin here. And what I wanted to point out is the precipitation and the results, when you look at 2,000 meters, 5,000 meters, and CLRH, are pretty different here in this watershed because the precipitation does vary spatially. The total precipitation volume is the same. We would expect 6.47 or 6.48 inches for all three methods because we're using the same precipitation. But the loss volumes and the excess volumes are going to be different between these. And that's because with the CLRH method, what we're doing is we're averaging the precipitation intensity across all the grid cells, right? So if your constant loss rate is 0.1 inches and the area averaged precipitation is 0.9 inches or 0.09 inches, then you get no runoff. With the mod CLRH method, we're doing computations on each grid cell. So if this rainfall in this grid cell is 0.2 inches, then we have excess, versus if it was 0.05 in this grid cell, then we have none. Okay, so there's a difference spatially with these methods, and you just have to be careful if in your watershed for the events that you care about, if there's variability in the spatial precipitation, then you can't go with the CLRH method. If there is some variability and you have a large subbasin area across the watershed, you're going to find there's probably little differences in 5,000 meters versus 2,000. So you can see the peak discharge here. So with my 2K model, the peak discharge is 870 CFS. And here for the 5K, it's 755. So there is a difference there. But there's a trade-off. The runtime, so let's check the runtimes here. The runtime I know for sure for the 2K model is over a minute. The runtime for my 5K model, let's just run that here. I believe it was 20 seconds. Yep, it's going to be around the 20-second mark. So what I'm getting to is even though there's some noticeable difference between these two methods, the 2K and the 5K grid cell size, you do make up for it in runtime. And even though the differences are there, you would still have a chance to modify the parameters in that model. So you can still get accurate results. It's just you're going to get to those accurate results faster with a shorter runtime. That was 30 seconds. Okay. So that's your kind of your homework there. Experiment with different discretization cell sizes. Another is, let's keep going. Yep, we captured that in the notes. If you do change the transform method, then you'd have to recalibrate your typical loss rates. Use the monthly average ET method. It doesn't require temperature, so that's going to be faster. I know sometimes temperature information can go missing, and it can be a pain trying to get or find that temperature information. So if you want to save time, move over to the monthly evapotranspiration method. But I have it in the notes here. I run across this a couple of times. Be careful about linking the same MET model to multiple basin models. And the reason why that's the case is HMS does a lot of checking behind the scenes. And if there's a change in one, so let's say I make a change to the MET model, but that MET model is being used by 3 basin models, then HMS is doing a big check to see if the results in those other basin models, any simulation that references those, is still valid. So the point here is if you see a lag, sometimes when you make a change to in a zonal editor, take a look at the MET model, see if it's being referenced by multiple basin models. And if it is, you can switch the include subbasins option from yes to no, so that MET model is only referencing the basin model that you care about for that forecast simulation. Okay. And then the last thing I have here, the Muskingum-Coons routing method is super computational burdensome. You're going to notice that that one probably takes up most of the runtime for a forecast simulation. So my suggestion or consideration that you should think about is switching over to the variable lag or K, or the Muskingum method. Okay, the Muskingum method and the variable lag and K are basically the same, but what you get from the variable lag and K is you can vary your Muskingum K and your Muskingum X based on flow rate, right? So you could create a simple relationship between flow and travel time. So you can back that into using velocities, right? So you can use your velocities from different flow rates to compute an array of travel times. And then as you calibrate the model to different events, you're going to have a better feel for how the attenuation factor, or the X factor, varies based on flow rate as well. So just something to consider. If you notice your computations or the message log from a HMS forecast, you're going to notice that it spends a lot of time going through those Muskingum-Coons routing reaches. Okay, I'll stop there. Any other questions or comments out there?
Yeah, okay, well, I guess there's no more questions for Matt. Matt, what would you kind of look for them to do during this session? Just trying these different resolutions, merging basins together, see how the model results, and varying the time step?
Yeah, anything that we talked about, I'd say is fair game. So what I'll do is I'll export this to a Word file real quick, and then email the group, and they can take a look and see if they want to just experiment with any of these options here over the next hour.
Okay. I'm going to open the breakout rooms, and I think we have it set up now to where everyone, so all the instructors can go from room to room to better support this time. So I'm going to open those rooms, and I think you'll just start getting thrown over there. But please let us know if you have any questions.
We thank you very much for your attention through this presentation. If you have any additional questions, would like help, or are seeking additional training, please feel free to check out the links on the screen that are also linked below in the description. If you'd like to stay up to date whenever more of these videos become available, please go ahead and like and subscribe, and you'll get notifications anytime more presentations or video walkthroughs are posted to this water management channel. Thank you so much, and have a wonderful day.